And you should be able to see my presentation.
Yep, it's working.
Perfect. Okay, cool. Well, welcome everybody. Thank you for joining us today. We're going to cover chapter 15, which is sequences, basically, and using RNNs. And then there's a little bit that they throw at the end where they actually use a convolutional neural network to do it as well. Sort of thing. And my name is Fouskarinis. I work in the healthcare IT field. I don't do this on a day-to-day basis, so I'm not claiming to be an expert in neural networks in general, but also recurrent neural networks specifically. It is a technology that I look at applying, and I've dabbled in the past in various different companies that I've worked in, but it's not my day in, day out job. So again, I'm leading this as somebody who kind of like you guys is, sort of just doing peer-to-peer learning. So if I misstate something or if somebody wants a clarification, please jump in, and that especially extends to people like Ted and Ryan. Okay, so what is today's agenda? So we're going to talk about what is a recurring neural network and kind of what makes it different to other types of neural networks. We'll talk a little bit about the issues around it, which are specifically things like unstable gradients, unstable weights, the fact that a plain vanilla one doesn't remember very long. It does have a memory, but it's not a very long memory. We'll talk a little bit about trend and seasonality, which the book doesn't really emphasize very much, but I think is an important thing to sort of draw out. I will just basically summarize the performance through of the different networks that we create through the book. I'll briefly mention other models, and then I'll also go a little bit into applications, because to me, I'm always more interested in how do I apply this technology? How do I improve the business rather than the technology itself? So I look at it more as a tool. And so my interest is more in understanding this against other models, and then what are its applications. Okay, so let's start off with what is a recurring neural network? So it's basically a neural network where you've got the different layers that are feeding forward, hence a feed-forward neural network. However, with the exception that it actually takes some of the feedback or some of the output, and it feeds it back into itself as an input as well. So the first diagram that you see here is basically a very simplified version where I've got basically one single neuron, one node, and it basically showing that I'm going to feed in some input. Could be a stock price, could be a word from a sentence or something, and then it's going to create an output. So it's going to make a prediction, basically, but it's also going to take that prediction, it's going to feed it back into itself for when I pass in the next value, right? And so there's this concept that so one of the important things is it operates on sequences. And so that is one of the things that differentiates a recurring neural network from others, is that you need a sequence, and a sequence is an ordered list of items, right? So for example, if I'm feeding in a stock price, I can't just feed in the stock prices in any random order. I have to feed them in the order in which they occurred in time, right? If that's a time-based sequence. If, for example, I'm doing some sort of natural language understanding, right, machine translation or something like that, then I have to feed in the words in the sentence in the order in the correct syntax. I can't just jumble up the words and just feed it in. So the concept of a sequence is very important for a recurring neural network. And then to that point, as I've already kind of alluded to, there's this concept of unrolling in time, right? So what this diagram on the bottom is basically showing you is that it's that same one single neuron basically over time being fed information. And I'm going to give you an example of this in the next slide. But any questions so far? No? Okay, cool. So let me give you an example of this, right? So if I take a time-based type thing, right? Again, using this concept of unrolling, it's the same neuron. Right? Again, I'm just using a very simplistic example here. It's the same neuron. And what I'm going to do is I'm going to look at the price of Coca-Cola, right, over, let's say, 5 days. And that's, if I put it in tabular format, that's what it looks like. If I graph it out, that's what it looks like, kind of thing. And so what I'm going to do is, in this unrolling little picture that we have here, at time t-2, right, sort of thing, I'm going to feed in the first value, right? And then it's going to calculate something. It's going to make a prediction, but it's also going to then take that and that prediction and then feed it back into itself. So in t-1, the next step, I'm going to feed in 61.38 as the price, but it's going to remember something about, it's also going to feed itself in some information about the previous price, which was 61.05, and the prediction that it made it's going to feed in the prediction that it made based on the 61.05 that I fed in previously, right? So based on the output from the t-2 step, it's going to feed that into the t-1 step. And then we do that again and again and again, right? So for every step in time, we're going to basically feed in the new input, but also feed in the output from the previous time step. And so that's this concept of unrolling. And it'll become really important for us to understand that, because when we train the model, we need to unroll it, and then we'll do back propagation through the unrolled network. But we'll come to that in a second. Okay, continuing on with what is an RNN. So that was kind of, I gave you a very simplistic version. So adding a little bit more understanding, a little bit more sophistication to the understanding, one thing to become really aware of is that the thing that I'm feeding back to itself does not necessarily need to be exactly the prediction, right? It can be some version of the prediction, some scaling of the prediction. And if I'm just using a single input, so a univariate input, then it may be some scaled version of it, right? But if I'm using multiple inputs, multivariate, right, then it may be some combination of those inputs, right? Some scaled combination. And that's where the weighting matrices will come in, which we'll get to in a second. But not only that, the cell itself can actually be more complicated. We're going to visit this in a second. So this is kind of a little bit of a preview, but not only is the thing that I'm feeding back into itself, right, this hidden state, what we're calling the hidden state, which I'm basically feeding from one time step to another, but it's still feeding it to itself, right, just between time steps. But that hidden state can actually be quite complex in the way that we calculate it. And I've got two examples of cells here that illustrate that, which we'll visit later on. But one of the things that I'll mention now, and I'll mention it again later, is the FC boxes, the fully connected boxes. They're actually miniature neural networks in and of themselves, right? So as you can see, this is starting to become a little bit more complex. Okay, and then another layer of complexity. Well, obviously, a single neuron is kind of limited in what you can do. So each layer, right, becomes multiple neurons, sort of thing. And then you might actually end up stacking layers as well. And we do go through that in the book, sort of thing. But that's now the full thing. So you've got multiple cells. Those cells can be as complicated as one of those GRUs or LSTMs, combining multiple inputs at the same time, sort of thing. And multiple layers of that. And then basically what you have is you have a weighting matrix for the X input. You also have a weighting matrix for the hidden layer, the thing that you're feeding back, right, in order to calculate the output. And then the output is basically a bias term plus a scaling of all of that, a scaling factor. Okay, any questions on that? So far, so good? Okay, I'll continue going. So last slide in kind of what are RNNs and just defining them. So not only did have we looked at how, complicated they can be, just a single cell of it, right? And then start, creating multiple cells, layers of multiple cells and multiple layers of cells. But you can also have different configurations. So one of several configurations is what we call a sequence to sequence. And this is where I feed in over time, a bunch of things, and I get a bunch of predictions out. And I might be interested in that if I wanted to, for example, get multiple stock prices, which is the example that we use, that he uses in the book, that the book uses, right? So I want to be able to feed in 50 stock prices, and I want to be able to get 10 future stock prices out. So that would be an example of sequence to sequence. Sequence to vector might be if I feed in all of those stock prices, but I only want the next one. I don't want the next 10, I just want the next one. Another example of a sequence to vector is if I feed in a sentence and I predict the sentiment, right? So is this a positive sentence? Is this a positive review? Or is this a negative review? That would be another good example for using a sequence to vector, right? Sequence to vector to sequence. This is something where I might feed in one or two values and then just let it loop on itself based on those one or two inputs. And so that's something that might be good for generating music, where I feed it a couple of notes, one or a couple of notes, and then it starts to generate a melody on the basis of that. And then the last one that's in this configuration here is the sequence to vector and vector to sequence, or the encoder decoder. So this is something that's really good for something like machine language, because basically what you do is you feed in the sentence from one language, it encodes it into some sort of internal representation, and then it decodes it into the target language, sort of thing. So that's an example where we're going to take a sequence, turn it into some sort of a vector, feed that vector into the next neural network, which will then translate it into the other language. Okay, so with that, the last slide in the in defining RNNs is basically, this is just for reference. If you want to go look up, the APIs in Keras, this is the URL, and the ones that the book mostly focuses are on these ones: the simple RNN, the LSTM, and the GRU. There's a couple of others that they throw in there as well, but this is an example of how you would create a 3-layer model. Again, lifted directly out of the book, so I'm not doing anything new here. I'm just extracting things out of the book. But basically a 3-layer model where the first 2 layers are a simple RNN of 20 nodes, and then it feeds it into a final RNN of 1 single node effectively, which you could have just used a fully connected layer as well. So it generates 1 output. So this is the example where they're feeding in a time series of values, and they want to predict what is the next 1 value in that time series. Okay, so what are the advantages and disadvantages of using an RNN over other things? So one of the advantages, obviously, is that it can process inputs of arbitrary length, right? So I can feed it a sequence of 50 stock prices or 2,000 stock prices, and it can process it. Likewise, I can feed it a sequence of arbitrary length sentences, for example. With that goes hand in hand the fact that the model size doesn't increase with the size of the input. So it's independent of the size of the input that I'm feeding it. Because again, remember, you're just going to feed it 1 value in at a time, right? And then recalculate 1 value in at a time, recalculate. So the model doesn't change in size. And again, because of the nature of the model, because it's using that hidden state where it's feeding it forward into the next time step, or feeding it back to itself, if you want to think about it that way, the computation takes into account previous history. Now, the last one I list here is both a pro and a con, an advantage and a disadvantage, is that the weights are shared across all time. So remember earlier in the mathematical equation that I showed you, you've got 2 weighting matrices. You've got the one for the input and the one for the hidden state. Well, it's because, again, if you just take the very simplistic model of it's a single cell, it's the 1 set of weights for the input, the 1 set of weights for the hidden state that are being calculated across time. And used again and again and again across time. There's not a different set per time step. It's the same ones for every single time step. I also consider that, just to jump to the cons, a negative, because it's the same set of weights across time. So, right, good in terms of training, bad in terms of it's not going to be a very flexible, right, sort of thing. And then it suffers from some issues that we'll get to later on. Another disadvantage is that it's computationally slow, and you'll see that and understand that in just 1 slide, because of the way you have to actually do the back propagation, right? Calculate all of those weightings. It has a short-term memory. So I read somewhere, I don't remember where, I wish I could find the reference again, but when I was doing my research, I read that a plain vanilla RNN remembers about 10 steps. Now, there's other things we can do, and we'll address that. So how do we address the short-term memory with some of those other things that I've already shown you, some of those more complicated cells? But the plain stock standard vanilla RNN kind of remembers maybe up to 10 steps. And that the other thing is, because of the nature of the topology of these things, it doesn't know anything about the future. It only knows things about the past. So generally, that may not be a problem for prediction, but on things like interpolation, for example, if I give you a sentence and there's 1 word missing in the sentence, it's not looking, if you're using this kind of a neural network, it's not looking forward, right? It's not looking at the words past the thing that you're feeding it in, right? So it doesn't know about any of the other context. Okay, any questions there before we move into how to train an RNN? Nope, okay. So training an RNN. So remember, we went through the example or the graphic of unrolling, right? So feeding in a sequence, feeding in all of those, whatever their stock prices or whatever, to get the final prediction. Well, the way you do, you adjust all the weights and you train this neural network is you basically do that. You feed it the sequence, right? So in the book, they use a sequence of 50 points. So you feed it all 50 points, 1 at a time. So you feed it the first point, let it calculate. Feed it the second point, let it calculate. Feed it the third point, let it calculate, right? All the way to 50. And then when you get to 50, you basically calculate your loss function for the 50th point, right? The 50th prediction, right? Then you adjust your weights, right? You do you calculate the gradient and you adjust the weights, right, for the 50th one. Then you go back one. So now you're unrolling the unrolling, you're undoing the unrolling. You go back one to the 49th. Again, you calculate the loss function for your prediction on the 49th, adjust the weights, go back to the 48th prediction, calculate the loss function, adjust the weights, all the way back to 0. So you have to basically, so why is this computationally intensive? You have to basically unroll the whole thing and then one at a time, roll it back and calculate the weightings for each one of those. And remember, you're calculating the same set of weight. It's the same weighting matrix for the input, the same weighting matrix for the output. Actually, sorry, the hidden state, I should say, the hidden state, and the same bias for every time step. So that's why it's computationally intensive, which was one of the disadvantages that I just listed.
Hey, Stephen, a minor technical note. So training RNNs is considered slow, and it's very difficult to parallelize this process where, like you said, you go from the 50th to the 49th, for the 48th, for the 47th, and just keep going all the way. I think technically, though, when you calculate the gradient on the 50th one, you don't apply it yet. You just store it, and then you calculate the gradient on the 49th, and you go all the way to 1. And then once you have all of those gradients, then you actually change the weights. I don't think you actually change the weights as you go, each one.
Okay, and then I may have misunderstood that. I thought you were doing it on a per time step basis, but in reverse. Okay, cool. Okay, so then what are some of the issues with RNNs? So one of them is, again, the gradients, and we'll see why in a second. So you have the problem of both vanishing gradients, things that go to 0, things that explode, and because the gradient is greater than 1, sort of thing. You also have non-convergence, which is a typical issue with the neural networks. And there's ways to deal with all of that. As I mentioned earlier, one of the disadvantages is that a plain vanilla recurring neural network does not have a very long memory, about 10 steps, sort of thing. So there's a couple of ways to deal with that, and we'll look at LSTMs and GRUs as ways of dealing with that. And then the other one that the book doesn't really touch on very much, but I wanted to pull out, is trend and seasonality. And you don't have to remove those, but generally it's an easier problem for the neural network to learn, right? It's an easier pattern for it to recognize if you do pull them out. So it generally improves performance, doesn't have to, but that's something else that we'll talk about as well. So let's talk about unstable gradients for a couple of slides. So one of the problems is you have the vanishing gradients and non-convergence. And for that, the book suggests that the usual tactics for deep neural networks will work, which is make sure you use good parameter initialization. So ideally randomizing them, sort of thing. Make sure you use an optimizer like Atom or something like that. You can use dropout as well, and that should help with the vanishing gradients problem and also non-convergence, sort of thing. Vanishing gradients, I'll explain in a second, but it has to do with the next thing, and you'll understand in a second. So one of the things that's unique to recurring neural networks is that ReLU, right, the activation function ReLU, actually makes things worse. So ReLU is the first one at the top here on the right, the diagram, where if it's negative, it goes to 0, and if it's great, and if it's positive, then it's just a 1-to-1, right, sort of thing, or some scaling perhaps, but for this example, it's a 1-to-1. Part of that problem, of course, is that it then leads to two problems. If you have very, very small values, then as you multiply it over and over and over again for the weightings of the previous one and the previous one and the previous one, as you work your way backwards, a very small value becomes even smaller very quickly. And then you also have the opposite problem, which is if it's greater than 1, right, then you potentially also have exponential explosion. Right, so ReLU is not really great for that, because if I'm multiplying by 2, then every time I multiply by 2, and as I'm going backwards, sort of thing, then it's 4, 8, 16, boom, 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 right, and it's exploding really, really quickly. So that's the runaway, right? So one way you can try and work around, runaway weights is you can just use a really small learning rate, sort of thing, but that's not necessarily guaranteed to fix it. A better way, and the reason why, for example, if you use Keras, by default, the activation function is hyperbolic tan, is to use saturating activation functions, right? And the two most common that are used are the sigmoid and the hyperbolic tan H, sort of thing, and they're shown here. And they're pretty much the same shapes, but it's just, do you want it to be positive or negative, or just positive kind of thing, right? sort of thing. And then you have the same problem with, so again, if you're using ReLU, you have the same problem with the gradients as well, right? So anything greater than 1 will explode a gradient. Anything really, really small will diminish a gradient. And then we also have the typical neural network problem of if you go to 0, then that weight becomes dead, or and you can't react. You can't resurrect it, right? Once it's 0 as well. So for that reason, again, one of the tricks that's used here is you try and use gradient clipping, right? So that you don't get your gradients exploding. Any questions on that? Cool. Continuing on with, yep.
That was a really good explanation. I just wanted to comment that, like, if you had a RNN with 50 time steps, you kind of have the same problems if you have a 50 layer deep anything else, a 50 layer deep CNN, if it, ResNet 50, whatever. But the difference is in a ResNet 50, all the weights are different. And so some can be more than 1, some can be less than 1, and they can, if you're lucky, they can kind of cancel out, right? But because this is just one RNN, if the weights on average multiply things by 2, then every one of those 50 layers is going to multiply by 2, and 2 to the 50th is a very, very large number.
Mm-hmm.
So yeah, exactly what you said. But just pointing out that these are the same problems that people have been worrying about with deep neural networks. It's just with RNNs, it can get even worse. Again, just because you're going to see the same weights over and over again.
Yep. Yeah, one way of thinking about an RNN is you can take like a deep neural network and then turn it on its side, right? With the really key exception is it's the same weight matrix at each layer, right? Not a different weighting matrix at each layer, right? So if you take that into account, then it's just basically a 10 stack deep neural network tipped on its side, but with the same weight matrix over and over again. And that's part of what makes ReLU not work well here. Okay, speaking a little bit more about unstable gradients. So the other thing that doesn't work really well to help, one of the typical tricks that we use with deep neural networks to help with the gradients is that we use batch normalization. But there's a reference in the book, and I reproduced the reference here at the bottom of the slide, basically saying that because it's this, again, same weight matrix, and you're doing the same normalization at every step, it doesn't really work very well. And the diagram on the right will help you understand in a second. And the reference here to that IEEE publication is that it's only slightly better than if you had done nothing, right, using batch normalization. What does work better is if you use layer normalization. So what's the big difference? So the big difference between layer normalization and batch normalization is when you do the normalization. So normally, if you noticed in the previous neurons that we used, there's the linear combination layer, that summation layer sort of thing, and then it would feed straight into an activation layer. And then you would do the normalization, right, after the activation layer, which might also be before you feed it into the next layer, right? So the output of one layer could be the input to another layer. But the point is that the summation goes straight into the activation, or the linear combination layer goes straight into the activation layer, and you don't have a chance. Well, linear layer normalization, basically inserts that normalization process between those two steps, right? So first I do my linear combination, and then I do the layer normalization on basically the features. Then I apply my activation function, which is either going to be tan H or a sigmoid, and then I output my results, right? And that seems to work much better for recurring neural networks. And that is something that's specific to recurring neural networks. So basically the difference is in this diagram on the right compared to what you had seen before is that circle in the middle, the LN, the layer normalization, would normally have been after the activation function. So those three circles there are, it's the linear combination layer, or the summation layer, layer normalization, and then activation. In other cells, that layer, that normalization happens after the activation function. Here we're putting it in between. Okay, so that's unstable gradients. Let's talk about the other issue for a couple of slides, which is the short-term memory issue, right? So I mentioned already a couple of times that a plain vanilla RNN can remember about 10 steps sort of thing. And again, if you think about back propagating those, the weights and the gradients kind of thing, again, it's 2 to the power of 10 roughly. So it makes sense that after a certain number of steps, there's really not much impact of the previous values, sort of thing, right? So one way to get around that is something called an long short-term memory cell, LSTM, and they're still quite popular in the literature and used quite a bit. And basically, it gives better performance. But what it does is it introduces two hidden states effectively rather than one, right? So instead of one, it introduces a second one. So there's a long-term hidden state and then a short-term hidden state, or a long-term memory and a short-term memory, right? So the long-term memory being the CT, and then the short-term memory being the HT, which is what we had seen before, the hidden state, right, HT. And then basically what it does is it introduces some gates where each one of those FC boxes in that diagram in the bottom right is actually a mini neural network, right? And it's a fully connected layer that is calculating the value, or a matrix probably, for that gate, right, for that function. And that function basically depends where it at, does different things. So the forget gate basically says, that long-term memory, which bits of that long-term memory do I want to forget? So if I have a multivariate input, if I have multiple features that I'm feeding in, so for example, if we were going to predict the weather and we're feeding in both the temperature and the humidity and the pressure and cloud cover and stuff like that, we might generate that function might end up generating some sort of a matrix that basically says, well, at this step, I want you to forget about the humidity, for example, right? Sort of thing. It's no longer becoming relevant, kind of thing, right? Sort of thing. So that's what the forget step does as far as the long-term memory is concerned, right? The input gate, basically, which is the I, basically says which parts of the prediction to add to the long-term state. So the latest prediction, do I need to add something to my long-term memory or not? And it functions the same way as I just described for the forget gate. The output gate basically says which parts of the long-term memory should I add to my output and to the short-term memory as well, right? And as I mentioned earlier, each one of those FC boxes is basically a mini neural network. One note that I'll also highlight from the book is, in the book they mentioned, and when I referred to the APIs as well, that if you are going to use LSTMs, it's preferable to use the LSTM layer, so the LSTM API, rather than an RNN layer passing in an LSTM cell. And the reason for that is because if you have a GPU or you're on a machine that has a GPU, the LSTM layer is written in such a way that it can take advantage of the GPU and parallelize some things, whereas the RNN layer is not written that way. So if you pass in an LSTM cell, it's just going to be on the CPU, and it's going to take as long as it takes, and it won't parallelize at all. So that's just a minor point that I thought was worth highlighting from the book. So that's one type. But as you can see, that's pretty complicated, right? Just for this one, effectively cell, neuron, right? We have now introduced 4 mini neural networks that live inside of it in order to be able to do this calculation. And of course, remember, all of this, we're going to have to calculate, use backpropagation to calculate weights for all of those, right? So this became even more computationally intensive than it was before, but it performs much better, right? So then later on, somebody came along, again, dealing with short-term memory, and said, you know, we don't need all of that complexity. We can get rid of, you know, the forget gate and the input gate sort of thing, and just use fewer gates, right? Sort of thing. So it's basically a simplified LSTM. It's called a gated recurrent unit cell. And it goes back to having only one hidden state. So instead of there being a long-term memory and a short-term memory, it's just got the hidden state, the what we call short-term memory for argument's sake, sort of thing. And then again, the remember gate basically says which parts of the hidden state of the previous state to show in the main layer, and then the forget and input gates basically say which parts of the previous state should I add to the prediction. One of the weird things, that one minus thing there that it does, and the book speaks about this, is if it is going to add something to the output and the hidden state, it kind of removes it from the G gate, which is basically your calculated prediction, right? Before it adds it into the output state. Okay, so I think the thing to take away from this is that there are 2 types of cells that you can use to basically help with the short-term memory problem. LSTM is still the one that I see. So this one, the more complicated one, is the one that I see in the literature sort of thing. Not that I look at the literature that frequently, but I still notice things, especially when I was doing some research to put this presentation together. LSTM is still mentioned fairly frequently. GRUs are not, for some reason. And I don't understand why. Ted and I were talking about this offline. It's just, if I was going to pick one, I would pick the GRU because it seems like it would be faster to train and right, simpler to understand. But for some reason, everybody still uses LSTMs.
That's my experience as well. I have trained plenty of LSTMs and GRUs, and performance has almost always been nearly identical with the GRU, just maybe being slightly faster. So my preferred one has been GRUs for a while, but the difference between them is kind of minor.
Yeah. Again, thing to know, guys, is if you need a better memory than a plain vanilla RNN, use a GRU or an LSTM. Right. Of course, I will speak in a few slides about overall what other models you might be able to use, but we'll come to that in a second. Okay, great. So that was one of the other issues, and then one of the things I wanted to highlight specifically from the book, that it's really just a sort of like a throwaway in the book. They give you one little box, they talk about it, and then they don't really talk about it, is trend and seasonality. And the approach is that basically, if you can remove the trend and the seasonality through regression and through differencing, then it's an easier problem for it to calculate. It's just calculating the variation as opposed to having to learn the trend and learn the, also learn the seasonality. There's a nice graph, matrix that I found here, little table that I found that kind of gives you a really good sort of visual understanding of how the trend interacts with the seasonality, right? So you've got four different trends that it shows you. You've got just a flat trend, you've got a linear trend, you've got a dampened or sort of logarithmic type trend, you've got an exponential trend. And then if the seasonality is additive, this is what it looks like. If the seasonality is multiplicative, this is what it looks like, kind of thing. And so so the general best practice is to try and remove that out, because it'll just make the job of the recurring neural network a little bit easier. You don't have to. But it's also not guaranteed to improve the results either, is the point that the book was making.
I would add to that, like your example earlier, talking about stock prices, like that's something I think a lot of people have tried. Mm-hmm. And if you just think of the example of, if you were trying to directly predict stock prices, and let's say Apple's at whatever, 2000, and then across time, it's actually going up, for example, mm-hmm. and then you try to use that model again in a month, that model is probably going to be no good, because it's going to see a value higher than it's ever seen before, and it'll just be out of range and it won't be able to do anything. But if you change the format of the model to be, what's the change tomorrow? So tomorrow it's going to go up 1% or $5 or something like that, then it's a much more general pattern that it can hold on to for much longer. And it's the same across all of the different stocks too. You don't have one stock that's 2000 and another stock that's 50 cents, for example. And it makes it much easier to learn, and it makes it much more stable too.
That's a really good point. Thank you for pointing that. Yeah, that's really helpful. Thanks. Okay, and so then the next thing I want to do is, so I kind of went through the book and I just picked out some of as the book was developing, the more sophisticated models, in succession, and how well was the performance? Because one of the things I remember from when I did one of these courses at university a while back, was the professor always told us that, look, if you think there's something there, just do a linear regression, start with that. If the linear regression says, yes, there's something there, then you can get more sophisticated, but don't bother building a sophisticated model until you know that there's something there. And a linear regression is good enough to give you an idea if there's something there. And I've seen this borne out a number of times, and that's why I'm always curious as to how well does one model perform against another. So they start off with a naive forecasting model. And if you recall, the naive forecasting model is basically, I'm just going to take the last prediction and say that's going to happen exactly again, right? I'm just going to be stupid about it. What was the stock price yesterday? Well, the stock price is going to be the same today. Sort of thing. And believe it or not, that gives you a mean squared error of 0.02. Then they do a linear regression on that, and they get a much better mean squared error, right? Okay. Then the book goes through the example, and they basically set up the, one single little neuron for the recurring neural network, and its performance is much worse than just a straight out linear regression, right? And it's not until they actually go to, they call it a 3-layer, but it's really a 2-layer, right? So it's 2 layers of 20 nodes in the recurring, in the RNN, with the last layer basically being just a single node RNN layer, which effectively could just be, like I said, a fully connected layer, just to output one single value, right? Sort of thing. And at that point, they get a slightly better error than just the straight out linear regression. And then the last one that they touch on was basically a convolutional neural network called WaveNet, where it's actually a stack, 3 stacks, and each stack being 10 layers deep of a one-dimensional convolutional neural network. And all they say is that this performs better. Now, I didn't have time to go and run the code to see how much better it performs and actually calculate the MSE. But that's all. That's quite a complex topology to outperform just a simple linear regression. And the thing that I wanted to highlight here is in the book, it actually, says that, WaveNet performs better than the RNNs, but that's for this specific case where they were trying to predict, a randomly generated sequence of 50 points, right? It really comes down to just depends on your particular use case and your application as to whether WaveNet would or wouldn't perform better, whether an RNN would perform better or something else would perform better. So it's very much case dependent. But in this particular case, I was just really curious about the fact that in the end, it was a convolutional neural network that performed better. Now, that's a really nice segue into, because one of the things that I was always fascinated about, as I said from the very beginning, and in general in this field, is what are the other models that are used to do sequence, especially time sequence, predictions, right? So one is the weighted moving average, where you give more weight to the things that have happened recently than previously. Another one that used to be kind of state of the art back a few years ago was ARIMA, which is the autoregressive integrated moving average. So it's a moving average where it's doing a regression against some previous values, and you specify how many values back you want to do the regression against. And it's also the integrated part is where it's trying to remove the trend and the seasonality, right? So that used to be the case. And then we already talked about in the book about WaveNet sort of thing. Some of the things that I found that were really interesting as far as this is concerned, and this is one of these examples where, again, RNNs were hot like 2-3 years ago, and they're not so hot anymore because now the hot thing is transformers, and apparently maybe transformers are looking better, but it's an evolving field. So, back in 2018, somebody had published a paper, I think it was in IEEE, showing that, LSTMs outperform ARIMA, which used to be the sort of state of the art, right? And then in 2021, I found it was a little side project, not necessarily a paper, that basically says that that a transformer was able to outperform an LSTM on a time series. And again, both of these, the reason I put in the words for time series is because it's for this particular application. So for sentiment analysis, for language translation, for something else, this may not hold true, but in terms of the time series, it does hold true, right? So again, the field is evolving. What was cutting edge 2 years ago is not cutting edge anymore, and everyone has kind of moved on to LSTMs and then moved on to transformers kind of thing. So that was basically the point of this that I wanted to show out. And there's a couple of references there if you want to go read up on it, which is interesting. Okay, and I'm kind of getting to the end of what I wanted to sort of discuss with you guys, which is, so the last thing is, what are some of the interesting applications, right? So obviously, this is, remember, the whole thing about an RNN is it's a sequence, right? It relies on a sequence. Now, that sequence can be time-based, right? So it can be things like stock predictors, speech to text kind of recognition, right? So as I speak, the words come out. It can be natural language processing, which is, the ability to either understand language or be able to translate from one language to another. One of the ones that we had used at a company about 3 years ago that we had done is we, again, had used simple sort of sequence prediction to kind of predict medical events. So if you feed me, the number of visits or the number of dollars over time that somebody has spent, from a healthcare perspective, can I predict whether this person is going to have any events in the next 6 months, right? Or they're going to be a high spender, right? They're going to cost me a lot over the next 6 months. So that was kind of an interesting application. Really, it was just a case of like, do they fit some sort of a predefined model where we've seen this kind of person before, and now that we're matching it against this kind of pattern kind of thing. So that was an interesting one. I found another one while I was doing research. I think it was a guy in Vietnam was looking to basically predict using RNNs the water level for a river that was flowing into I think an ocean or a sea. I don't remember which one. but into a large body of water, where the water level in the river would be influenced by the tide itself. And he was able to actually get pretty accurate predictions just by using an RNN on past, tide values kind of thing. I thought that was an interesting prediction, an interesting application. Other applications for sequences that aren't necessarily time-based, the ones that I've talked about so far are time-based, is generating image captions, right? So I can feed it in an image and it can generate a caption for that image, sort of thing. So that's not so much time-based. Another one that's, you could argue is still time-based, although I would argue it's really more just the sequence of the postures, is it's kind of like moving posture recognition. So if you click on the reference there, it'll take you to somebody who basically used LSTMs, right? One of the types of recurring neural networks, to basically be able to predict whether somebody was walking, whether somebody was going upstairs or downstairs. So it's kind of like a dynamic posture recognition, right? Pose recognition. And then the last one, which I didn't expect to find, was somebody basically published a paper in IEEE about using an RNN to recognize Chinese handwriting. So rather than taking the usual approach, which is you throw a convolutional neural network at it to kind of decompose it into lines and edges and all that sort of stuff, this guy was basically saying, I can just take a recurring neural network and apply it to the strokes as well, right? Or some representation of the strokes. And that was kind of an interesting application as well. So again, things that were sequences, right? A sequence of strokes or a sequence of movements or a sequence of images, sort of thing. And there's some unusual applications beyond just the ones that everyone always thinks about, which is stock prices. Okay, and with that, I will thank you very much and open it up to questions, and I will do as best as I can to answer them.
Thanks, Stephen. That was a really good overview. All right. Do people have questions?
No, probably sounds not. Okay.
So with the Chinese handwriting recognition, you're looking not at the complete character, but just at the individual strokes as they're being written. Is that?
I think, if I remember correctly, it was over a week ago now that I had found it. I think that was the case. Yeah.
Okay. Yeah, that would make sense, because that would make it sort of a time series rather than just an image recognition task. Really cool.
Which only a Chinese person would have thought of, right?
Yeah.
I do have a question, Stephen.
Yes.
There was a slide you had on the pros and cons.
Yep.
And I was wondering if you could go over the cons for the weights being shared across time. I didn't understand that one too well. Why is that a con?
Because it can't really learn by local, again, I'll give you my answer and others who are more experienced can jump in. Because I come up with a set of weights that have to apply across the whole sequence as opposed to just part of the sequence. So maybe if I'm looking at a sequence, right, so if I'm going to make something up. So let's say I'm looking at stock prices, right? There might be a part of, if I look at the stock price and I look at it as a graph over time, there might be a part of that graph that has kind of a little predictable pattern to it. Right. Well, I can't create a weight matrix that just focuses on that thing with a neuron that basically says, oh, I see this pattern, I know what's going to happen next, right, and be able to predict it. You have to come up with a weighting that's going to work across the entire sequence. Let's say I'm feeding in 1,000 stock prices, 1,000 points, right? It has to work across the whole sequence. So it doesn't have any of that locality built in, whereas things like transformers and other types of neural networks, but especially transformers, they can pay attention to just certain chunks of the sequence and not necessarily have to come up with a single weighting matrix that is going to work across the entire sequence, right? And that's also why it becomes more important to be able to remove the trend and the seasonality out of it as well.
Hey, Stephen, if I could add to that, like if you think about languages, in English, at least, there's definitely some sort of bias, like the subject of the sentence tends to come near the beginning of the sentence. It doesn't tend to be at the very end. And so you might not want to do something completely different to understand the words at the end of a sentence than the beginning, but you could imagine you might want to do something slightly different, but an RNN is incapable of doing that. It cannot treat the first word or the second word any differently than it treats the 10th word or the 11th word, because like Stephen said, it's just processing everything one at a time the exact same way. And it doesn't even know when it's going to end. So when it's on the 8th word, it doesn't even know, is that the last word or is there 50 more coming? Because it's just got that very narrow one-time slice view. Does that make sense?
So it's kind of like the weights may be shared at let's say there's an instance where the weights are shared at a higher value than they need to be, or that then is necessary. Is that what you're saying?
I'm saying that you're going to train it so that it learns, and assuming you're using like a more advanced one like an LSTM, it's got some memory, it's got some history, okay, but it doesn't really have position as one of its inputs. So it can know like, oh, there was this word boy 2 words ago, but the same effect is going to happen whether you have boy 2 words ago at the very beginning of a sentence or the boy 2 words ago at the very end of a sentence. But you could imagine that maybe there's a level of sophistication if you take into account not only, hey, there was the word boy 2 words ago, but also where are we overall in the sentence? And that's just not possible in a simplistic recurrent architecture.
Thank you.
So Stephen, if you don't mind, I'm going to grab the screen share for a second. So I just did a quick search. I hadn't done this in advance, but this is Papers with Code, and next week we get introduced to the transformer. I'm not going to put Vibhu on the spot, but you know, the book doesn't go that deep into transformers. If we look at transformers, there's going to be 80 jillion papers about transformers on Papers with Code. Most of them since this book was published in 2019. But I just looked up LSTMs, and if you scroll down here, you can see there's 375 pages worth of papers being referenced, and I sorted it by date, and so the most recent ones are here, you know, from February this year. There's clearly no shortage of people who are still using LSTMs. I think you tend to see them as more as building blocks in a bigger, more complex architecture. It's not just like, hey, I took my inputs, I fed it into an LSTM, and I took out the outputs directly. You know, so like you may be processing video and you may have a CNN that's doing frame by frame, and then the embeddings that's coming from that CNN, you might then feed into an LSTM network because the frames of a video are clearly in a time sequence. So I thought I would just sort of share that like even after we talk, actually it's 2 weeks, I think I might have said next week, in 2 weeks, about more about NLP and about how transformers are more powerful. People are finding them to be more powerful than things like LSTMs and RNNs. People are still using them. I'm not a researcher. I'm not sure why. I don't know if sometimes it's just they're smaller, they're faster, if it's just because out of habit people want to try it. You know, transformers are kind of expensive in terms of compute time. And then also, if I click this link about recurrent neural network, you'll see that Papers with Code shows the different names that people have given to various tweaks on the basic RNN. So George in the chat mentioned the bidirectional LSTM. And so what you can do is, if you have a fixed length sequence like a sentence, you can certainly feed the first word, second word, third word, fourth word, and the LSTM will have context information about all the words that came before it. But you can also have one that goes in the reverse direction, where you feed the last word, the second to last word, the third to last word, and it's going to remember, as it were, things that are to the right of that particular word. So if you have a bidirectional LSTM and you have both of those, the forward and the backwards, at any point in time when you're looking at a particular word, it has sort of the memory from the left as well as from the right. There's some of these that I don't necessarily know exactly what they are, but you can see here the LSTM and the bidirectional LSTM in terms of the number of papers, what we were talking about. GRU is 10 times less than LSTM, but Ryan, Stephen, we don't know why. And they have bidirectional GRU also. Conv LSTM is kind of what I was saying about a video, where you take a CNN and you process things, and then the output of that goes into an LSTM over time. And then I don't know what some of these other things are. Wave RNN, SRU, QRNN, LMU, snail.
If I can hop in for a second, one of the reasons why we still see a lot of LSTM papers and LSTMs being applied over transformers, well, I'm not sure actually if the book will go into too much detail about how transformer networks work, but one thing is that they're pretty deep and they need a lot of data to get going. Like, they're built on an attention mechanism, and you need quite a bit of data to like actually get anything useful out of that. In a lot of cases, you don't have a lot of data, you just have something small. So your transformer network might not really get anywhere, whereas just slapping on like a little LSTM model, you'll actually see results faster. So one thing is data. Second, as you mentioned, is obviously the compute time and the resources that you have allocated. So there's still that reason. And then as some of these things you start setting, like the bidirectional LSTM, all that stuff still applies to LSTMs. Like, a big background of transformers is the attention mechanism, but we still see papers where they're applying attention to LSTMs. So like, there's always middle grounds. You can do like LSTM plus attention layers if you don't have that much data and whatnot. But yeah, one of the things with transformers is just you need a lot of data, which in some cases we don't have, and compute is another one.
That's really great. Thanks, Bibu. The data thing, I think I was thinking that the other day, I totally forgot, but that makes tons of sense. If you only have 10,000, 20,000 training examples, you can't afford a more powerful thing. It's just going to overfit.
And also people will use like pre-trained transfer learning. They'll use transfer learning. So they'll take like a pre-trained transformer model that might know like a language very well, but then to slap on and fine tune, you might not have as much data. So you can use something smaller like an LSTM to just fine tune it towards your specific use case. So I think it's still pretty fundamental to know. And another reason why there's just a lot of papers, you can see like this LSTM paper started in 1997. GRU started in 2014. So there's just a lot of history back there. Like, I think back when I was in college, we like calculated LSTMs and those old ARIMA models by hand, did the math, like for exam by hand. So like, it's still like in that curriculum, whereas stuff like attention, you can do it by hand. I've done it. It's just, it's not there yet, you know, but then there's still papers that will like work on these old school techniques. And the fact that it's still being taught by hand in school, you know, like papers will always be there on that.
Yeah, that's awesome. Thanks, Bibu. By the way, that reminds me, since you mentioned the ARIMA, Stephen showed a couple links. And I would say anytime you see a paper, research paper really about anything, and they say, hey, our performance was better than X. I would generally speaking take that with a grain of salt, One thing that I've seen is people will spend 6 months doing research, trying every possible permutation, every hyperparameter tuning option, tweaking the architecture, and they will get a 1% performance improvement, over, whatever, say an ARIMA model on a time series. But they didn't put in that equivalent effort to try to get the ARIMA model to work really well. They just took it like vanilla out of the box and said, hey, look, we beat ARIMA, So I would say up until at most the last 6 months, whatever, I would say that the standard time series models, ARMA, ARIMA, SARIMA, were considered state of the art, and that no form of LSTM transformer, whatever model could, on average, beat their performance. I think now we've started to see a few very complex, very large transformer networks where you can say, hey, I can apply this to just a generic unseen time series problem, and I may be able to expect to get equivalent or ever so slightly better performance than the more traditional time series models. Any other comments or questions?
So I was just curious. I noticed Hobson posted something about retro. Do you know, can you give us a 30-second overview? I've never heard of retro before, so.
Google just released it this week. They've been working on it for 3 years, ever since GPT-2 and 3 came out. It's their answer to GPT-3. They believe that they have a lot of other sparse attention, and they've been working on a lot of more efficient ways to do attention in transformers. And this is their latest attempt. What it does is it actually just combines their search technology with a neural network. So they actually train a network to find the most similar passage to what it's trying to say at the moment, and spit out the actual passage that a human has typed. And their accuracy is actually better in most cases than on many of the benchmark transformer problems than GPT-3, especially for generative problems and question answering.
Cool, thank you.
It's still a transformer. It still relies on that sparse big bird transformer attention architecture, but as the core, but it's 100 times smaller, that particular model. And as it starts to generate text, it quickly finds a good match among its corpus of possible things to say. It still requires massive data. Obviously, they're doing web scale search in order to find those passages.
Actually, Kathleen has posted a question. Can anyone speak to the need for the time series to be a stationary process, and whether RNNs can handle non-stationary processes? So we did cover that in one of the slides, Kathleen. So the answer is you don't have to, but generally they perform better if you remove that was the trend and the seasonality thing, right? So the trend being the stationary aspect. So it's an easier problem to solve, and it's more generalizable if you do, but you don't have to.
Yeah, Stephen, I haven't actually worked on it, but my guess would be that maybe an RNN will be okay with linear trend. I don't know. I mean, but some more complex trend, yeah, you're just making your life difficult. I think, to use the technical term, if you can turn your data into stationary data, you're just making your life a lot easier. And then hopefully you'll need a simpler, smaller, faster model to predict that. And then once it makes its predictions, then you can reverse the process that you use to make it stationary to get back into your original units.
And whatever power your network does have for non-stationary data can be reserved for the actual essence of the data that is not stationary after you've done all the things that you know are going to get it as close to stationary as possible. So that you're basically doing all the hard, all the messy work first by making it stationary and allowing the model to focus on that stuff that you're not able to do because you don't know how the world's going to behave in the future. Because if it was purely straight stationary, if it was purely a stochastic process, then you've gotten all the pattern out of the data entirely, and there's nothing left for the machine to learn. And whatever that model is that you use to create that stationarity, that's where the pattern is.
Yeah, I always think about physics. I think about ballistics when thinking about something like this. So if you threw a baseball or shot a cannonball, you know, we kind of, I think all in math classes have seen that it's like going to follow the shape of a parabola, right? So if you just vanilla took those data points in, or any kind of decently powerful model would sort of learn how to predict parabolas, right? But if you said, hey, I'm going to do some work and I'm going to see if I can make this, you know, something that's a little simpler, and you actually took out that, you know, the basics of the parabolic thing, then in fact, what you would find is that it's actually dealing with the air resistance. And so then your model could spend all of its energy predicting the air resistance as opposed to having to figure out the parabolic thing in the first place. And so your model could just be that way more accurate, since you did, like Hobbs was saying, you did the hard work of figuring out that big trend. And now it can spend its energy on more finer details.
Awesome example.
Going back to the stock example, I think it's a matter of what you're focusing on. So like with my example earlier, talking about Apple, imagine their stock price is $2,000 or something like that. Is the important thing that you're looking at how it changes, or are you trying to actually predict the actual magnitude? Is it more important that you're close to getting it near 2000 again? Or are you actually trying to measure the difference that it goes up $5 the next day or something like that? And so if you actually care more about the difference, then you do want to make it predict the difference directly rather than the actual magnitude.
Totally.
Thanks, Ryan.
And
So go ahead, Hobbs.
I was going to say the time series forecasting is always usually very, very short term. And so it's only that change that you can ever really predict accurately anyway. So there's no point in looking at any other information. All the other information is just noise, because it's determined by things that your model just doesn't even have visibility into, externalities.
Hobson, can you define what you mean by short term?
Well, Google calls it nowcasting. They're basically only able to forecast the weather with machine learning models very, very like an hour or two in the future. NOAA models walk away from the truth over days, and yeah, your accuracy is proportional. It grows exponentially with time, basically, on all, just because of the nature of recurrent neural networks. As you build up error with each prediction, the next prediction is going to be that much worse, and it's going to random walk away from the truth in an exponential curve. The time constant of your problem depends on the time constant of the dynamics that you're trying to predict.
Thanks.
And then if I could just add one more comment, since we're talking about stocks, the weather is sort of a closed system. The stock market is not a closed system. And so I think a lot of people who first hear about machine learning think, well, wouldn't that be great if I just got it to predict stocks and then I could get rich pretty quick, right? But the problem is that there are people who have information that you don't have. And it's it's not a whatever, just a fixed closed system in that regard.
But by closed system, you mean there's no external influences. So like when Goldman Sachs figures things out, they go and buy stuff, and that's an external influence on the market. Is that what you're talking about?
Yeah, and the fact that whether it's illegal or legal means, they are obtaining a lot of information that you don't have. So even if you think that I built this very sophisticated model that has 100 data points for every company, trust me, they have more. And so I always find it interesting when like people say like, oh well, if you know machine learning, you should just predict stocks, and then what, why bother getting a job? Just do that and then retire. And I think that's the main challenge, is that the other guys in general who do it for a living know more than you do about everything.
Yeah,
Just a
even
quick comment on that. It always struck me that a large difference between predicting stocks and biomedical or weather or something like that is the presence of an adversary. So I'm not disagreeing about hidden information, but you can argue that that weather has hidden information. You don't know the micro temperatures in lots of places. So in some sense, there's also hidden information. Not disagreeing with your point, but I actually think the presence of an adversary just means that you actually need to think of weird models that your adversary is not thinking of, and it becomes primary. Whereas in weather, as far as we know, God is not doing that to us. And so, we don't have that game being played. Anyway, just a side comment.
That's a very
Cool,
good point.
thanks, Dan.
It's like the stationarity thing we're talking about. Your adversaries have taken out all of the patterns that are in the data already. They call it pricing it into the market. So all of the knowledge, everything that everybody knows in aggregate, the wisdom of the crowds has gone in there and priced the stock as to what the collective consciousness thinks it's worth. And it's really, really hard to be smarter than that collective consciousness.
Well, the other thing, especially with the stock market, is you've got two, important influences. And one of those is, there's things that happen that you would never have imagined. Like GameStop is a really good example of that, right? You could have built whatever model you wanted, and then a bunch of people just decide, you know what, we're going to just F with the system, right? We're just going to screw with the system, sort of thing. And then the other thing is you've got these things called humans that are very unpredictable and irrational, right? That really factor in as an externality, right? And then I'll actually add a third one. The third one is sometimes there's, I'll call it hidden forces, for lack of a better word. And that's kind of the same thing as what I think Dan is talking about, which is a good example is this week, NVIDIA apparently posted great results and their stock dropped. And everyone's scratching their head trying to figure out, we don't get it, right? They beat expectations, they did everything right, and then the stock dropped anyway, going back to the point about the irrational humans, right?
Well, I think that comes down to that old saying in stock trading, the trend is your friend. So if you're in a down market, it doesn't matter, right? The trend is downward and you're going to get sucked down. And that's probably what happened to NVIDIA or any other company.
So we're actually at 1:30. Hold on a second here.
Somebody's typing.
Yeah. So we're actually at 1:30. So we're going to transition now to the second meetup that we have every Saturday. So we can actually continue talking about RNNs or talking about time series, because the second one is just project discussion time. So it's open-ended. We can continue talking about these, but it also means that some people who don't join the book club drop in at this time, and they can come and ask questions about projects they're working on, if they're having coding issues or anything like that. So just going to pause here. Yeah, so everybody, please, thanks, Stephen, for, again, volunteering to be the discussion leader and doing a nice recap on this chapter.
You're very welcome. You're welcome.
Yeah. So next topic, Vibhu is going to continue talking about sequences, but really focus on natural language processing, and transformers are introduced, which these days, if you're at all interested in deep learning, you can't not know what a transformer is. So that's super critical. So that'll be, again, in 2 weeks. Next weekend we're alternating weekends. So next weekend is the next session in the graph data science series. Okay, so if you're not staying for the project discussion, if you're just here for the book club, you can feel free to drop here, and then we'll stop the recording.